Welcome back, focused learners. Okay, be honest with me. Have you ever looked at a massive, multi-page organic chemistry textbook and just felt completely overwhelmed by all the naming rules? Yeah, we've all been there. But you are in the exact right place today. We're going to transform those dense, seemingly impossible rules into an easy-to-follow, highly visual guide. Think of this explainer as your master key to finally decoding the language of chemistry.
Because, well, here's the fundamental challenge, right? How exactly do you give a unique, universally recognized name to a massively complex molecule? We're talking about molecules with fused rings, branches going absolutely everywhere, and multiple functional groups all just fighting for priority. So for this explainer, I want you to step into the shoes of a chemical detective. Your job is to read a molecule's highly specific, internationally recognized legal identity. Because trust me, every single number, every single syllable has a distinct purpose.
Okay, let's dive into this. Here is the mental roadmap we'll use to logically conquer these rules. First, we're going to tackle alicyclic ring compounds. Second, bicycloinspiranes. Third, aromatic benzenes. And finally, translating names to structures.
Section 1. Naming alicyclic ring compounds. We're going to start right at the foundational rules for isolated closed rings, which chemists call alicyclics.
Now, what's really fascinating here is this concept called the lowest sum rule. Take a look at this substituted cyclohexane. We essentially have two different ways we could number the carbon atoms in this ring to pinpoint where the ethyl and methyl groups are. If we start numbering one way to give the substituents the positions 1, 1, and 3, well, the sum of those numbers is 5. But if we take a different path around the ring, we get 1, 3, and 3, which adds up to 7. So what does the IUPAC rulebook say? It dictates that the legally correct name is 3-ethyl 1,1-dimethyl cyclohexane. Why? Because 5 is lower than 7. It is a strict mathematical pathway to make absolutely sure there's only one valid name.
But what happens when that ring is attached to a long chain of carbons? Who gets to be the main parent name and who is just the sidekick? The rules are surprisingly straightforward, actually. If the ring has an equal or greater number of carbon atoms than the side chain, the ring wins. It's the parent. That makes it an alkyl cycloalkane. Now, if the ring has fewer carbons, the chain wins, becoming a cycloalkyl alkane. But wait, there's a massive trump card here. If the side chain contains a functional group or a multiple bond, that side chain automatically wins the parent title, regardless of how many carbons it has. The ring is instantly demotic to a mere substituent.
And speaking of functional groups, they command the absolute highest priority of all. Take a quick look at this comparison. Depending on whether a functional group is acting as just a minor prefix or the absolute primary suffix, its name actually changes. For instance, the COOH group is just called carboxy if it's a secondary player, but it becomes carboxylic acid when it's the principal functional group dictating the identity of the entire molecule.
Moving right along to Section 2, bicyclo, tricyclo, and spiranes. Let's see how this builds into something even more complex as we step up from single rings to fused ring systems.
Check this out. This is bicycle 3,2,0-heptane. The word bicycle straight up tells us there are two fused cycloalkane rings sharing two or more atoms. We call those shared atoms the bridgeheads. But look closely at those brackets, 3, 2, 0. What on earth do those mean? Well, to name a bicycle compound, you literally count the number of carbon atoms in each bridge connecting the two bridgeheads. On one path, there are 3 carbons. On the other path, there are 2. And straight down the middle, directly between the bridgeheads, 0. And you always list these in strictly decreasing order inside the brackets.
So the crucial trick here is knowing how to walk the legal pathway around this molecule when assigning numbers to substituents. You must start your numbering exactly at one of the bridgeheads, no exceptions. From there, you are legally required to proceed along the longest bridge first to get to the second bridgehead. Then you continue back through the next longest bridge, and you finish up by numbering the shortest bridge last. It's like a highly structured walk around the molecule.
Now contrast that with spiranes. Unlike bicyclo compounds that share multiple carbons, spiranes are polycyclics that share only one single carbon atom. Because the entire structure is pinched together at that one single point, the numbering rule completely flips. Instead of starting at the shared carbon, the numbering absolutely must uniquely start next to the fused carbon, specifically inside the smaller, lower-membered ring. You number around the small ring, through the shared carbon, and then finally around the larger ring.
All right, Section 3.
aromatic and substituted benzenes. Let's shift gears to our third logical block, where chemistry actually respects a little bit of history.
For a lot of learners, this next concept is a huge aha moment. When you're dealing with substituted benzenes, you actually don't always need to construct these super complex, clunky systematic names. IUPAC officially accepts a lot of historical, common names as the legal base compound. For example, a benzene ring with a methyl group. We don't just call it methylbenzene. The accepted name is toluene. Pop an amino group on there, that's aniline. A methoxy group gives us anisole. So just recognizing these base names is going to save you a massive amount of effort.
Now, when we start attaching even more things to that aromatic ring, the rules shift depending on how crowded it gets. If a benzene ring is di-substituted, meaning exactly two substituents, we often use the trivial prefixes. You might know these: ortho for positions 1 and 2, meta for 1 and 3, and para for 1 and 4. But once that ring gets tri-substituted or higher, we throw those prefixes right out the window. We go right back to identifying the substituents, putting them in alphabetical order, and applying our trusty lowest locus sum rule.
And this brilliantly illustrates exactly how universal that sum rule really is. Look at this tri-substituted benzene. We've got a bromo, a methyl, and a nitro group. If we number it one way, our substituents are sitting at positions 1, 2, and 4. Add those up, you get 7. If we go the other way, they sit at 1, 3, and 4, which sums up to 8. Because 7 is lower than 8, the officially binding IUPAC name is 2-bromo, 1-methyl, 4-nitrobenzene. The exact same logic we learned for simple rings applies perfectly to these complex aromatics.
Okay, Section 4, translating names to structures. We've reached the climax of our explainer. We know how to build names from structures, but a true chemical detective has to be able to reverse engineer a massive, terrifying name right back into a physically drawn structural formula. To do this, there is a critical 5-step procedure that turns a totally daunting block of text into a simple puzzle. Step 1. Find the root word. This dictates your longest carbon chain. Step 2. Check your primary suffix to see if you're dealing with single, double, or triple bonds. Step 3. Place your principal functional group using the secondary suffix. Step 4. Drop in all your prefix substituents at their specific numbered locants. And finally, Step 5. Add your hydrogen atoms to satisfy carbon's valencies. Let's actually walk through a wild example together to see this in action. The name is 6-bromo, 8-hydroxy, 4-ethoxy, non-6-enol. I know, it sounds absolutely terrifying, right? But watch how easily it falls apart. The root is non. That tells us it's a 9-carbon chain. Boom, draw 9 carbons. The primary suffix is -ene at position 6, so drop a double bond between carbons 6 and 7. The secondary suffix is -ol. That indicates an aldehyde functional group right at the end of the chain. Finally, look at the prefixes. We just stick a bromo group at carbon 6, a hydroxy at carbon 8, and an ethoxy at carbon 4. Just like that, the whole puzzle is solved.
Now, once you've placed all your puzzle pieces, you actually have a choice in how you present your final drawing. You could use the stick formula or the bond line formula. The stick formula is where you explicitly draw out every single carbon atom in a row. The bond line formula, on the other hand, uses a zigzag line where every single point or bend just represents a carbon atom. It is so much cleaner and honestly a lot faster to draw.
But listen, here is the absolutely vital distinction you have to remember. If you choose to draw a stick formula, you are legally required to manually add your hydrogen atoms. Every single carbon must have exactly 4 bonds to satisfy its valency. So if a carbon only has 2 bonds showing, you must draw in 2 hydrogens. Bond line structures, however, beautifully assume those hydrogens are already present. Any chemist reading it just naturally knows they're there. So, look at what we've covered. We did the lowest sum rule, the strict bridges of bicyclomolecules, the accepted historical names of aromatics, and that 5-step puzzle method for reverse engineering. You have completely mastered the progressive rules. So I just have to ask, are you ready to act as the chemical detective all on your own? I'm going to leave you with a provocative thought. Take a look at this. This is molecule number 5, right out of Concept Application Exercise 1.2 from our source material. It is a massively, heavily substituted benzene ring just staring right at you. Based on everything we just decoded together today, what do you think its base name is? Where exactly do you start numbering? I challenge you to apply that lowest sum rule and decode this molecule's true legal identity all by yourself. Thank you so much for joining me on this explainer. Keep practicing those naming rules, and whatever you do, never stop learning.